LLC, USA. Fran has worked in the field since the beginning, with 29 of those years at SRI International, and he now has his own lab. Fran's plenary talk is 30 minutes and is titled Some Novel Analytical Techniques Applied to LENR Active Materials. Let's turn it over to Fran.
Okay, thank you, Steve, for that introduction. I'd also like to thank the organizing committee for inviting me to give this paper. To the attendees, good morning, good afternoon, good evening, as we've all said. Since there has been a lot of discussion on finding the best material for LENR, I've decided to talk about methods to determine the properties of the materials used and take the opportunity to introduce you to some new techniques. The outline is self-explanatory, so I'll only point out that there's a natural break between SEM and EDX, with metallurgical and physical properties such as optical microscopy, density and porosity measurements, terahertz measurements, and the aforementioned scanning electron microscopy in the first half of the talk. The second half will cover chemical and elemental measurements such as energy dispersive X-ray, ICP, optical emission spectroscopy, ICP mass spec, and helium mass spec. Then I will end with a rather old worked example of designing and manufacturing a palladium rod from measurements like these. Let's get started. The old-fashioned optical microscope can tell you quite a bit about your materials. Here are the micrographs from two pieces of Brillouin's 3-layer coated tubes. These have been cut in a diamond saw, mounted in an epoxy casting resin, and sequentially polished from coarse grit sandpaper down to 1 micron diamond paste on a buffing cloth. The upper left photo shows the cross-section of the tube after mounting and polishing. The white inner ring is the tubular substrate below the first coating of copper. The lower left photo shows the tube mounted lengthwise with a metal shim holding it at about 4 degrees from horizontal, so the polishing exaggerates the depth radially. In the middle micrograph, you can see the outer 2 layers of dielectric and nickel, as well as the epoxy, with voids evident inside the dielectric. The micrograph on the right shows the copper from the oblique cut sample, exposing its grains and grain size. Here we see professionally mounted and polished 3mm palladium cathode after a lithium deuteroxide electrolysis experiment from SRI. The palladium grains and grain boundaries can be seen in the 2 micrographs. The middle micrograph is about 130 microns wide, while the higher magnification one on the right is 52 microns wide. I've turned off the color saturation and adjusted the exposure for better contrast in these 2 micrographs. After electrolysis, the grains are about 5 microns. You can also see the grain boundaries in both micrographs. Normally, you should make note of the grain size and orientation before use via non-destructive microscopy for later comparison. On this slide, I show 2 instruments similar to those that were used regularly to characterize solids and powders at SRI. Although these instruments are normally used for catalyst and catalyst support materials, they can give you important information about pure metals or metal ceramic composites. Understanding the physical voids and internal surface area of cathodes and gas-exposed solids is important, as we are all learning from recent discussions in the online forums. For pure materials, the measured density tells you what the percent density of the material is, as very often these materials are not 100% dense. Knowing the non-molecular absorption or adsorption, that is not what's in the interstitial sites, allows one to better calculate how much of the hydrogen isotopes are in the interstitial sites. You can also do metals analysis through stress strain instruments. Another important physical measurement tool is X-ray diffraction. A powder or solid sample is held in a monochromatic X-ray beam while an X-ray detector is swung through an arc of 90 degrees or more. The diffracted beam intensity is plotted against the angle in 2 theta. Generally, the resultant peaks are compared to a very large database of known diffraction patterns. Impurities much below 1% are generally missed by this technique. The 3 major peaks are from the face-centered cubic lattice of nickel. The minor peaks are from the alumina powder impurity, since this nickel was scraped from a nickel coating on top of alumina. The structure of unknown materials created during the LENR process may be determined using something called the Rietveld refinement, which is much better than the old ways we used to do powder diffraction analysis. Recently, we at Brillouin and Anthropocene have been introduced to the terahertz imaging technology practiced by my co-author, Rahman, at Applied Research and Photonics. His email address is given on the final slide. This slide is here only to show that this technology yields the same results seen via SEM and TEM on 14 nanometer metal lines deposited on silicon wafers. The image on the left shows a 2 by 3 micron slice of the image sample, of the terahertz imaging sample. The one in the middle is a 1 by 1 micron slice. The graph on the far right plots the grayscale density versus horizontal position across the middle image, the top being the black line, the bottom the white space. The full width half max of each peak used to calculate the line width averages to 15 plus or minus 1 nanometer compared to the nominal 14 nanometer lines. Published references for this work is shown at the bottom of the slide. It is important to note that this technique overcomes the Abbey diffraction limit of traditional microscopic methods. From a tube constructed similarly to that shown in the earlier optical micrographs, the outer nickel coating was analyzed using terahertz imaging. The sample in its holder is shown in the left photograph. The image in the middle shows the lines seen in 100 nanometer by 100 nanometer measurement. On the upper right is shown a 100 nanometer cube from the same measurements. Rotating cube images can also be produced. Applying this analysis shown on the previous slide, the full width half max measurement from this grayscale depth plot in the bottom right of the slide gives a significantly greater lattice constant as coded than found by scraping some of the powder off and running the X-ray powder diffraction shown. The plasma spraying process seems to have yielded nickel with a dilated lattice constant, or what we call lattice expansion. This level of expansion would yield a unit cell volume approximately twice that of pure nickel. Using the same samples, there were actually 4 samples used in both of these analyses, both in the imaging and the spectroscopy. Terahertz spectroscopic measurements were collected from 0.1 to 32 terahertz. The terahertz laser spectrometer setup and appropriate references are shown at the bottom. The absorbance spectrum from 0.1 to 10 terahertz is shown in the bottom right graph. Several peaks are noted in the range for those calculated for nickel phonon excitations. These are in a similar range to those reported by Dennis Letts in his dual laser beat frequency experiment on palladium. I'm not an expert in solid state spectroscopy, so I present this simply as a way to learn something about the phonons of solids used in this field. Feel free to contact Honest directly for more further information. These are close-ups of the same data from the previous slide, presented this time in wave number mode. The absorbance peaks are consistent with those reported in the literature for nickel oxide. We predict that the nickel was oxidized after leaving the spray gun and before cooling on the tube. Although the metal travels through a reduced atmosphere plasma at the spray gun, it travels room air on its way to the target tube. There is still some work yet to be done in understanding these materials before and after exposure to hydrogen in the reactors. I see many uses for this terahertz spectroscopy on any LENR material that's being used today. Now let's transition to scanning electron microscopy. Here are some SEM micrographs taken by Alan Goldwater down in Santa Cruz on Brillouin tubes similar to those shown earlier. The conducting materials show up as white and the insulators show up darker. The legend bar on both of the upper micrographs of the cross-section and oblique angle cut samples is 2 millimeters. In this mounting, the oblique cut, the vertical direction is expanded by a factor of 10 compared to that in the cross section. The legend bar on the lower left micrograph is 7 microns, allowing for much finer measurements than in my optical photographs. The green dots on the left side are for EDX elemental composition measurements that I will talk about in a few minutes. On the right is the same photo at lower magnification. The legend bar is 50 microns. Here is an example of a micrograph of a palladium foil cathode at much higher magnification, 5000x, post-experiment. This is from SRI's reproduction of Energetic Technologies superwave electrolysis experiment. This micrograph was taken at the Naval Research Lab, and it's obvious that you can see features of 1 micron. The legend bar there is at 2 microns. This sort of SEM can tell you quite a bit about a sample before and after exposure in a reactor. We now transition from the physical analysis portion of the talk to the chemical analysis portion. Energy dispersive X-ray analysis uses the X-ray energies of individual elements when exposed to an X-ray beam in the SEM's vacuum chamber. EDX of the same oblique cut sample shown earlier can tell you quite a bit about its composition. These elemental maps taken by Alan are a great visual aid in understanding what's going on in the multi-layer coatings. The aluminum dominates both the sprayed and extruded alumina map in the lower left image. The lowest place is the extruded material and the upper orange is the sprayed material. However, the 5 images on the right show the aluminum in orange and the oxygen in red separately. The carbon map is in yellow, and that's from the epoxy mounting resin. The thin blue map is of the nickel on the outer coating, and the green is from the copper of the inner coating. Another way to view this multi-layer coating is from the cross-section sample. On the bottom left is a thin section of an SEM image covering 682 microns horizontal. The line through the middle designates where the EDX spectrometer has taken elemental measurements along the image, which is a novel way to view the elemental constituents across a multi-layered coating. In the graph in the upper left, which aligns with the SEM image in the lower left, the red line designates the nickel composition, the blue line the aluminum in the dielectric, and the green line the copper coating. The voids in the image line up with the reduced aluminum strength in the graph. There is obviously some sodium impurity, yellow line, in the copper. The right side image shows the elemental analysis of different points, green dots in the SEM micrograph taken in the middle of the alumina coating. These were shown earlier. Although concentrations below 1% are suspect, notice the 1.22% sodium in the -2089 sample. That tells us that sodium impurity seen in the left graph is undoubtedly real. And we don't know where the sodium came from, but it's undoubtedly an impurity after post-experiment. It is interesting to note that the aluminum oxide ratio is relatively constant, even though there are several other impurities sitting on top of it. The alumina seems unchanged during its run. The carbon concentration seen is from the machine background or from epoxy that moved into the voids during polishing. A tool similar to EDX is X-ray fluorescence. It uses the same principle, measuring the X-ray energies of materials exposed to incident X-rays to identify the elements present in solids, powders, and even liquids. As with XRD and EDX, the results are usually compared to known library peaks. Impurities below the 1% level are generally not seen. The same powder scraped from the Brillouin coated rod and measured using X-ray diffraction shown earlier was measured using an XRF instrument at SRI. There are usually 3 different energies to cover the whole periodic table. I show the middle energy plot here, which contains the nickel K alpha and K beta peaks, along with a minor amount of iron. Other elements called out in the plot are not detectable. The lower energy plot, not shown, also showed the aluminum from the alumina impurity. Unlike EDX, no vacuum is necessary for XRF measurements since it is performed in room air. I'll apologize for the train noise next door. This office sits about 10 meters away from an active railroad. Carrying on in the chemical analysis theme, ICP optical emission spectroscopy is a destructive way to determine the major, minor, and impurity elements in a material. Because it obtains a spectrum from the emission of many elements, several elements can be analyzed for simultaneously as opposed to the old atomic absorption method. Concentrations in the part per trillion level are common from ICP-OES analyses. The numbers in this table have been normalized to the nickel major component. Results are usually test reported as part per million or part per trillion. These analyses and those on the next slide are from Cerium Labs in Austin, Texas. ICP-MS can tell you some of the same information that you get from ICP-OES, but also may tell you about isotopic changes in your material. Note that the results in the bottom line of the upper table. Here, it's showing a potential isotopic anomaly. The best way to assure isotopic analysis is to use good isotopic standards. The example shown here has not been verified, but is shown as a possible analysis example. In this case, the analyst felt that the mass resolution was not good enough to comfortably differentiate between nickel-64 and zinc-64 because there was no nickel-64 standard available. This is an oldie but goodie from SRI, first presented at ICCF-11 and represented yesterday by my former colleague, Mike McCubry. I show it here for another use of destructive metals analysis using mass spectrometry. As a reminder, the Aradajan double-structured cathode consisted of a thick-walled palladium bottle filled with palladium black. We procured 2 of them from Arada and electrolyzed 1 in heavy water and 1 in light water for 3 months. Brian Clark and Brian Oliver analyzed the helium-3 as an off gas from the melted palladium black and palladium wall from this double-structured cathode. Slicing up the wall as illustrated in the cartoon, they created a depth profile of helium-3 from the inner wall to the outer wall of the cathodes from both experiments. The results from the D2O experiment showed that the tritium produced in the inside diffused out, achieving the expected concentration gradient as it decayed to helium-3 along the way. A fair amount of tritium was also measured in the electrolyte from the D2O experiment. No tritium or excess helium-3 was measured in the light water experiment. So what can you do with this analytical information? First off, I don't expect you to read that whole eye chart there. This was an analysis performed by IMRA Japan on many cathodes, at least twice as many as on this chart, for chemical analyses shown here. They also performed several of the material and metallurgical analysis that I mentioned. 21 different elements were analyzed for. With the right capability, you can reproduce a desired material that may no longer be available. The details shown are not important, but using these chemical analyses, in addition to their other materials analyses, IMRA Japan was able to reproduce one of those materials. I show that in the upper photograph. Many other palladium rods were produced using these analyses for the NHE lab in Sapporo. In summary, I hope that I've shown you the value of these physical and chemical analysis techniques in documenting your better letter materials versus those less successful materials that you've tried. Optical and electron microscopy and terahertz imaging can tell you about the metallurgy of metals and metal ceramic composites. Density and surface area measurements can tell you about the available voids and spaces in between. The other measurements can tell you about the chemistry. In addition, you can produce these pretty pictures from the SEM EDAX. The ultimate point of this exercise may be to help us reproduce the materials that are best suited for use in LENR experiments, such as those shown 2 slides earlier, or to create and verify the properties of a material of your own design. Finally, I'd like to acknowledge Alan Goldwater for the use of his images and results performed for Brillouin. Alan is available to create such nice images and, more importantly, results for you. I'd like to acknowledge IMRA Japan for its analysis and palladium rod manufacture done for the NHE lab in Sapporo. Finally, I'd like to thank the Anthropocene Institute for its support, and thank you for your kind attention.
Thank you, Fran, for a very interesting presentation. We do have time for some QA. So if you have a question, please go to the reactions button at the bottom of your screen and raise your hand. I see we have some raised hands already. So let's start with Dr. Iwamura. If he can be unmuted, or as soon as you're unmuted, please go ahead and ask your question.
Yeah. Thank you. Thank you for a nice presentation. And would you show again X-ray fluorescence data?
Yes.
Yeah. I would like to know. You have a peak of nickel and iron, and you have another peak between copper and zinc.
That's actually the nickel K beta line.
Nickel K beta. Okay.
Yeah, the tall one is obviously the K alpha.
Okay. Thank you. Thank you.
Okay, Raj, you have your hand up, so you're next.
Yeah. Yeah, considering the importance of the surface and near surface region, characterizing the electrochemical surface area would have been useful, right? So even though many of the SRI samples are very well characterized, I've never noticed electrochemical surface area information. I was wondering whether it was attempted and or attempted, but you couldn't characterize the ECSA. Any comments on that?
I do not remember performing any of that, although I presume, well, yeah, we did have a tiny little scanning microprobe, but I don't remember using it on the foils. Most of the work that we did at SRI was actually with 3mm rods, which is very difficult to characterize the surface of.
Okay, thank you.
We do have 1 or 2 minutes, so if there's any other questions, please raise your hand now. I'll give it a few seconds, and if not, we'll continue on to the next speaker. If you do have any questions for Fran, please reach out to him through email.
Okay. I have a question, Steve.
Oh, go ahead. Go ahead, Ziki.
And I'm interested in the terahertz because it seems quite new for starting lattice expansion or strand.
Yeah, I was afraid you were going to ask that. I don't know if my co-author, Rahman, is online, but feel free to send me or Anis any of your questions. I'm obviously nowhere near an expert on either terahertz spectroscopy or terahertz imaging.
Okay, thank you.
Sorry about that.